The last circuit we will cover in this chapter is what we call differential amplifier with cascoded load. The cascoded circuit, as we discussed it in previous lectures, says that we will have very high gain. Because if you wanted to maximize the gain even higher, you can use cascoded amplifier. Basically, if you look at the circuit, the cascoded circuit, it's a little bit big circuit, but don't get scared. Let's look at it carefully. What you have here is the two transistors M1 and M2. M1 and M2 behave as current amplifiers. Basically, they will take the small differential voltage and they will give you large current through the drain. Then what we have is these two transistors, which are M3 and M4. M3 and M4 are biased at some particular voltage. We call it V bias 3, and these two transistors behave as voltage amplifiers. So basically they will take the current coming in from M1 and M2 and they will amplify it to a voltage at the output. So the type of amplifier here becomes common gate amplifier. Now the load has two stages. The first stage, which is M5 and M6, and then the second stage, which is M7 and M8. All these transistors are properly biased at V bias 2 and V bias 1. We make sure that each transistor pair is perfectly matched. So M1 is the same as M2, M3 is the same as M4, M5 is the same as M6, and M7 is the same as M8 in terms of the W/L ratio and the design parameters and the number of fingers for each transistor when you do the 2D layout. Then we can also use the half circuit approach, and the half circuit will basically look like this. If you will see, the circuit starts from the top with M7, then M5, then M3, then M1, and we have the input voltage, which is half a differential input Vn/2, and then we have the bias current, which is ISS/2. So this is basically the half circuit, and the gain using the half circuit symmetry is given as AV will equal to V out over Vn, and that is will equal to GM1 times GM3 times RO3 times RO1 in parallel with GM5 times RO5 times RO7. And it is obvious that this circuit will have a large gain because now you have much bigger output resistance than what we had before. The disadvantage is the cascoded amplifier requires large voltage overhead, and that will lead to a less output voltage swing range, and it utilizes large area, but the advantage is that it gives more gain. Now, something also you have to watch for is biasing the cascoded amplifier is challenging because you must guarantee that all transistors remain in the saturation region at all times. This particular circuit is a little bit tricky to design because in real world you have to also deal with the variation of the process parameters, how much the VDD changes. As VDD changes, all these transistors have to remain in saturation. How much the W/L changes due to the variation in the manufacturing parameters. As these variations change, you still have to make sure that all transistors remain in the saturation region, and then you still want to design the circuit to give you the maximum output voltage swing at V out and so forth, and it is a little bit challenging to design. Basically, this is the end of today's lecture, which is the differential amplifier. We discussed the basic differential amplifier, what does it do and how does it amplify the differential voltages. And that is very exciting because now we have actually looked at the input stage of the operational amplifier. Almost. The only thing we have to deal with in the next lecture is how to do the DC biasing. And once you understand how to do the DC biasing, you basically did the complete input stage of the differential amplifier. And this is exciting. So we are learning a lot of concepts, and they are very practical and they are useful, and some of us will carry with us to the job and to the field, and we will push and advance and implement new technologies as we continue, starting from today's lecture and beyond.